so I'm going to speak about revolutionizing industrial decarbonisation. We recognise the challenges jointly at this conference, the challenges brought to societies by climate change. CO2 capture today is too expensive, very much seen by businesses all over the world for good reasons as a cost center, rather than having the avenues developed for utilization options and turning that cost center into a profit center. And over 50% of sites do not have the space. We are very much focused at Carbon Clean on the hard to abate industries: cement, steel, petrochemicals, and energy from waste. Most of these are very mature industries with sites that can have been operating over many decades. So it is not so straightforward to simply bring in and deploy a large-scale carbon capture plant. Some of the solutions that we have focused on and will be bringing with our next generation technology, and we see this overall as really incentive for technology providers in carbon capture to focus on in the years ahead, is a $30 per ton cost for carbon capture. This is significantly below what is achievable today. 10 times smaller equipment size and 5% overall footprint reduction. In terms of the market opportunity, and we should really recognize that there is a market opportunity. This decade, up to 2030, there's a CO2 capture market of close to 530 megatons. And you see the breakdown on this slide: bioenergy, carbon capture and storage, chemicals, iron and steel, and in particular cement are large emitters of CO2, and opportunities are there in those industries for carbon capture. But most interesting of all, if we then look at the following 2 decades, is that cement will continue to be significant due to infrastructure development and growing populations, but chemicals in particular is set to more than double in terms of infrastructure, plants, and carbon dioxide emissions, leading to opportunities to capture that carbon dioxide. So there's a multi-billion-dollar market, and current estimates are very much saying that it can be turning into a $1 trillion market in the next couple of decades. How are we solving these challenges at Carbon Clean? You see here a high-level process flow diagram of the Amine carbon capture process. It's a well-known process, and essentially we have the flue gas coming into an absorber column. The amine solvent, which we have, is showered in from the top of the absorber column, and it is very choosy. It only reacts with the CO2. The resulting amine-rich solution with the CO2 then moves into the stripper column via a heat exchanger, and the process does require energy. So heat energy, typically provided by LP steam from a facility, heats up the solvent, and then you have 99+% pure CO2 leave the process. We can deal with the CO2, compress it, liquefy it, get it into the appropriate phase for any utilization that is planned. And then following the regeneration of the solvent, the lean solvent returns into the absorber column. A couple of values that Carbon Clean has been bringing to this process. Firstly, from our solvent chemistry, our proprietary amine solution, we are achieving much higher absorption of CO2 versus comparative technologies. And also, we're very focused on best environmental performance. We have undertaken long testing campaigns and shown that our solvent is emitting at the parts per billion level, so near zero chemical emissions. This is becoming a key topic in countries around the world, and any solution that we bring with regards to carbon capture has to be very focused on its overall environmental impact. Some of the solutions offered by Carbon Clean, and in general, how we see technology development progressing in this area. We are offering CDRMax technology today. CDRMax is the name of our amine solvent. So this is the engineered to order large scale plant deployments, a mature technology. Capacities can be in the range of 40 to 1,000 tons per day. We're certainly engaged on opportunities at that scale. But we see a drive towards modularization because of the footprint constraints and certainly the cost challenges in the industry. We are already offering a solution called Semi-Modular, and here we've been able to integrate most of the systems within the amine carbon capture process within a couple of containers. Because it is still the amine carbon capture process, you need to have the scrubber and the stripper column, which are seated nearby. But this solution certainly provides some schedule and footprint benefits. We have 38 of these units running in Germany for over 5 years in the biomethane upgrading sector. And most exciting of all from our perspective is the next generation technology. What is possible in terms of process intensification with carbon capture in the existing amine carbon capture process has largely been achieved. There is no further step change which is viable to a significant level. So we have come up with a technology called Cyclone CC, where we are utilizing rotating packed beds for the purposes of carbon capture. So the absorber and the stripper column are replaced by rotating packed beds within a machine. This is 100% modular and containerized solution. Your entire carbon capture plant will be within a single 40-foot shipping container. Capacities will be 5 to 500 tons per day eventually. We are currently testing at 3 sites at 1 ton per day in the US, in the UK, and in India. We are going to scale up a factor of 10 within the next few months to 10 tons per day with demo testing at customer sites, customers in the cement, steel, and petrochemical sectors. And then as we continue to develop this technology, we plan to scale up a further factor of 10 by the summer of 2022, where we will offer this to industrial users at least 100 tons per day, a 100 ton per day carbon capture plant within a single container. A little bit about product roadmap. Our solvent was demonstrated back in 2012 the APBS family of solvents from Carbon Clean. This stands for amine promoted buffer salt. Amine is the component that is reacting with the CO2, and then proprietary buffer salt design, which is regulating that reaction. We went through commercial demonstrations in the US, UK, and Europe in 2015 and received the necessary safety approvals. And if we fast forward to 2020 and beyond, where we are today, we have over 40 operating units capturing over 850,000 tons per annum of CO2. And of note, we have recently signed a joint venture with Veolia in India, and this joint venture will focus specifically on the energy from waste sector and biomethane upgrading. And then from 2023 and beyond, our focus, and we believe eventually the focus of other technology providers in the industry as a whole, is going to be focused on next generation modular containerized solutions, allowing us to get to this $30 per ton carbon capture cost with significant size reduction and overall footprint reduction. I've mentioned this number of $30 per ton a couple of times, and here is our rationale behind that. So if we take a typical amine process shown by the column on the left, nobody today talks about a carbon capture cost of less than $55 or $60 per ton. In Europe, it is even higher. It is north of 70 euros per ton of CO2 captured. And with our next generation containerized solution, we see some significant CapEx and OpEx reductions, allowing us to get to this $30 per ton target. So on the CapEx side, you lose the large absorber and stripper columns, these columns that can be 30 to 40 foot high. You lose many of the auxiliary systems and project costs involved with deploying a plant, a major carbon capture plant investment at scale. And on the OpEx side, there's a considerable reduction in the regeneration duty. So this is where you apply heat to the solvent to regenerate it. You are achieving intensification of the carbon capture process with centrifugal force. So your regeneration duty and requirement for heat is somewhat reduced. There are solvent makeup and waste disposal cost reductions and other OpEx savings. By other OpEx savings, again, on a large-scale plant deployment, there are going to be many consumers of utilities, electricity being consumed by pumps and motors. So, here's our rationale of how we believe we can get to $30 per ton as a carbon capture cost, which will make many projects that are currently unviable very much viable. A little bit about our references around the world. We have 38 units in biomethane upgrading in Germany, a number of CO2 carbon capture references in Europe and the US, primarily through the use of our solvent, and 2 industrial carbon capture and utilization references in India, and I will speak more about that in the next few slides. So utilization is a key part of the carbon capture process. If the utilization path is not figured out, then the project will not likely fly. One such opportunity is CO2 conversion to soda ash. India was the first to have a commercial plant where this is happening, a plant that was commissioned in 2016. And here you take flue gas, can be typically from coal-fired boilers. And through the process that I presented earlier, you are extracting the CO2, and with the addition of rock salt ammonia, you are producing soda ash. So you're converting CO2 into a green product, and that can be used for manufacturing either detergents, cleaning products, or even with the correct level of purification going to the food industry with examples such as baking soda. So the one reference I mentioned in 2016, the Tuticorin alkali chemical and fertilizer limited plant was commissioned. This is the world's first full-scale commercial carbon capture and utilization plant. And this plant was essentially buying in CO2 from the market in India, the gas market in India. And today they capture 60,000 tons of CO2 from the coal-fired boiler flue gas on site. The capture cost is just under $40 per ton, which is actually very competitive for the existing technology, but is achievable due to various factors, including the setting in India and the utility costs. Over 90% of CO2 is being captured, and this is being converted to soda ash and being sold to the likes of Unilever, who are producing detergents with this product. A very good example of the circular economy. I saw one of the colleagues on this conference reply on what a circular economy is for CO2 a little earlier, but this is a great example of that. You are taking your material from emissions and producing something with that of commercial value. Another opportunity for utilization that we see gaining a lot of momentum is the CO2 to methanol value chain. India, again, is very active in various initiatives to do with CO2 to methanol. And here you take hydrogen produced. It can be produced from electrolysis, of course. Green hydrogen has a much more significant sustainability profile. CO2 captured from industrial emitters. And this CO2 and hydrogen comes together to produce green methanol, and you can then move to fuel processing and convert that into specific fuels. So you have high quality carbon neutral methanol and a number of utilizing options. You can also consider, higher grade market options for that. And in terms of our most mature activity, we are currently working on a project called Liquid Wind in Sweden. This will be the world's first e-fuels facility. So we, with our technology, are capturing CO2 from industrial emitters within the area. Liquid wind will bring in renewable electricity. And we are partnering with companies to produce high renewable energy. And then essentially, via the methanol reactor, methanol will be produced and used as a transport fuel. It has already been announced by Liquid Wind in the public space that they have an offtake agreement with Maersk. So, it is helping these transport companies achieve their net zero targets. I'd just like to end with, some of the diverse companies we're working with, and that really as a way of showing the engagement that is going on and the market activity. So I mentioned the joint venture with Veolia in India, focusing on energy from waste and biomethane upgrading. We're certainly engaged with a major cement companies, Lafarge, Cemex, Dalmia, on carbon capture initiatives at various cement plants. I talked about liquid wind, CO2 to methanol, and then we're working with a host of other technology providers to bring these solutions to customers. So that concludes my presentation.
Well, thank you, Asam. This was indeed very clear in terms of the value proposition that you are bringing to the table. And I'm glad that we had the opportunity of listening to you this afternoon. As you would imagine, I have actually a flood of questions for you from the audience. I'm afraid we have time only for a couple of them, so I'm going to just sort of shoot them at you.
Sure.
So there's this question from Pratik Rajendra Borse. He would like to know, the question reads, what is done further ahead with the captured carbon dioxide?
Yes, so as I mentioned, utilization is key. If that is not well thought out, then the project likely does not happen. And there are a number of options. At Carbon Clean, we do focus on the core competency of the carbon capture plant, but we certainly partner with utilizations because that is important to bring to customers as an overall solution. So I talked about soda ash production and methanol production, but there are many other options. Aggregate production. A lot of the cement companies are focused on a circular economy approach to take the CO2 captured from the plant back into the material, so you can produce enhanced concrete by the absorption of CO2 within the concrete. And a host of others, greenhouses. It doesn't always have to be large scale, enhanced oil recovery. There are many options, and in this post-pandemic world, I see more options coming to the table for this crucial utilization piece.
Okay, great. There's another question which I think is related. It is from Mr. D.P. Misra. He would like to understand, what do you do with the stripper exit carbon dioxide? It's similar, isn't it?
It's the same answer, yes. So we have 99+% pure CO2. If the utilization was food grade, we could purify it further to get it to food grade quality. But then the answer is similar. Whether industrial grade or food grade, there are a number of options that we can think about and discuss with regards to utilization.
Yeah, and the last question we have time for is, what is the level of carbon dioxide removal from flue gas?
Yes, so that's typically 90 to 92%. And it then all comes down to economics. You could go for higher CO2 removal, but the investment that would be required to go for that extra, 4 or 5% would not really be economically viable. So 99 to 92% is what is achievable with current technologies, and certainly a good level to target from a economically efficient perspective.